In this video and the next, we're going to revisit the famous traveling salesman problem. When we first talked about TSP, it was bad news. The context was NP completeness. We discussed Edmonds' conjecture that it's widely believed there's no known polynomial time algorithm for solving the TSP problem. But let's talk about some good news, the fact that you can do better than naive brute force search. In fact, it's going to be another neat application of the dynamic programming algorithm design paradigm. So let me remind you briefly about the traveling salesman problem. The input, very simple, just a complete undirected graph, and each of the n choose 2 edges has a non-negative cost. The responsibility of the algorithm is to figure out the minimum cost way of visiting each vertex exactly once. That is, you're supposed to output a TOR, a permutation on the vertices, that minimizes the sum of the corresponding n edges. For example, in this 4-vertex pink network, the minimum cost TOR has overall cost 13. You could, of course, solve the problem using brute force search. The running time of brute force search would be roughly n factorial. This would allow you to solve problems with, say, 12, 13, maybe 14 vertices. In this video and the next, we'll develop a dynamic programming algorithm that solves the TSP problem. Now, of course, TSP is NP-complete. We have to respect that. We're not expecting a polynomial time algorithm. But this dynamic programming algorithm will run quite a bit faster than brute force search. The running time will be big O of n squared times 2 to the n. 2 to the n is, of course, exponential, but it's quite a bit better than n factorial. N factorial is more ballpark n to the n. Okay, if you look up Stirling's approximation, you'll see it's really n over a constant raised to the n, but still that's much, much bigger than a constant 2 raised to the n. To make it more concrete, you could run this dynamic programming algorithm for values of n probably pushing 30 or so. So I realize these are still pretty absurdly small problem sizes compared to the size of the arrays that we can sort, compared to the size of the graphs on which we compute strongly connected components or shortest paths, but that's how it goes with NP-complete problems. You have to work pretty hard even to solve modest-sized problems. So at least this dynamic programming algorithm proves the point that even for NP-complete problems, there are opportunities to improve over brute force search, and the programmer toolbox I've already equipped you with is sufficient to make some of those improvements. For the traveling salesman problem in particular, it's been a benchmark problem for the development of tools and optimization, and people have worked very hard to solve very large instances of the traveling salesman problem, even with tens of thousands of cities, even sometimes over 100,000 cities. But, I mean, this often represents years of work. As I said earlier, there's some really nice sort of popular accounts of the traveling salesman problem books out there. Check it out if you want to know more about the state of the art for solving large TSP instances. So I said we're going to pursue a dynamic programming approach to the TSP, so that means we should be looking for optimal substructure, a way in which an optimal solution must necessarily be composed of an optimal solution to a smaller subproblem extended in some easy way to the original problem. So what could that look like for TSP? So of all the problems that we've tackled using dynamic programming, I think the one which seems the most like TSP is single source shortest paths. So think about a TOR not as a cycle exactly, but as a path from some vertex, let's say vertex number 1, looping all the way back to itself, with of course the constraint that it should visit each other vertex exactly once en route. We want to minimize the overall cost of this path from one back to itself, so that sounds a lot like wanting to minimize the length of a path from some source to some destination. And I'm sure you'll recall that our dynamic programming algorithm for the single source shortest path problem was the Bellman-Ford algorithm. So what then did the subproblems look like in the Bellman-Ford algorithm? Well, the cool idea there was to measure subproblem size using an edge budget. So a canonical subproblem in Bellman-Ford was to compute the length of a shortest path from the given source vertex to some destination vertex v that has I edges or less. So, by analogy, we could think here about subproblems where we want the shortest path from the starting node vertex number 1 to some other vertex, j, that uses at most I edges. So precisely, let's define subproblems as follows. For a given choice I, this represents the number of edges that you're allowed to use. A given destination j, let's assume the vertices are just named from 1 to n, so I'll call a generic destination j an integer from 1 to n. Let's denote capital L sub ij as the shortest length of a path from the starting vertex 1 to this destination j using at most I edges. So suppose we try to set up a dynamic programming algorithm using these subproblems. What do you think? Can we use these to get a polynomial time algorithm for the TSP problem? All right, so the correct answer is C. So this proposed collection of subproblems does not yield a polynomial time algorithm. That is, D is not the correct answer. That would be surprising, right? TSP is an NP-complete problem, so if this gave a polynomial time algorithm, we could all report directly to the Clay Institute for our $1 million cash prize. Now, there's a lot of students in this class, but at least we'd each get 20 bucks or so out of the deal. So that's not the case. This is not going to yield a polynomial time algorithm. What's the problem? Well, the problem is also not A. It's not that there are too many subproblems. We only have O of n choices for I and O of n choices for j, so there's only a quadratic number of subproblems, just like in Bellman-Ford. That's totally reasonable. We also can correctly compute the value of larger subproblems from smaller ones. It's really exactly the same as what we were doing in Bellman-Ford. The problem is that our semantics are incorrect. By solving these subproblems, we don't actually get an optimal solution to the traveling salesman instance that we started with. So what are we hoping is going to be the case? Well, in our dynamic programming algorithms thus far, after we solved all of the subproblems, the answer to the original question was just lying there waiting for us in the biggest subproblem. So here the biggest subproblem would correspond to I equaling n, where you're allowed to use up to n edges in your path. The issue with these subproblems is they only specify an upper bound I on the number of edges you're allowed to use. They does not enforce that you have to use your full budget of I edges. So that means when we look at these biggest subproblems, yeah, the shortest paths could use as much as n edges if they wanted, but in general they won't. They'll use much fewer than n edges, they'll skip tons of the vertices, and that's not a traveling salesman tour. A traveling salesman tour has to visit every vertex once. That is not enforced by these subproblems. That problem doesn't seem so hard to fix. Let's just insist in each subproblem that instead of using at most I edges in the shortest path, it has to use exactly I edges in the shortest path. So while this set of subproblems is not quite as misguided as the previous one, the answer remains the same. The answer is still C. Of course, we still don't get a polynomial time algorithm. We're not planning to prove p equals np. The number of subproblems hasn't changed. It's still quadratic. And if you think about it, you can still efficiently solve for bigger subproblems with a bigger edge budget, given the solutions to all of the smaller subproblems. So what's the issue? The issue is that our semantics are still incorrect. Just because you solve all of these subproblems doesn't mean you can extract from it the cost of a minimum cost traveling salesman tour. So the problem, briefly, is that we don't enforce the constraint that you can't visit a vertex more than once. What were we hoping would be true? We were hoping that when we look at the biggest subproblem, so this is when I is equal to n, and we're looking at paths that have exactly n edges, and when we take j, the destination, to be 1, the same as the origin, we were hoping that that shortest path with n edges from 1 back to itself would be a tour, and therefore the minimum cost traveling salesman tour. But that need not be the case. Just because this path has n edges and it starts at 1 and it ends at 1 doesn't mean it's a tour. It might, for example, visit vertices 7 and 23 twice, and as a result, it never visits vertices 14 or 29 at all. For this reason, the number computed by the largest subproblem when I equals n and when j equals 1, that can be much, much smaller than the true answer for the minimum cost traveling salesman tour. A good algorithm designer is nothing if not tenacious, so let's just recognize the flaw in this proposal that we're not enforcing the fact that you can't have repeat visits to a vertex, and let's just change the subproblems yet again to explicitly disallow repeated visits to a vertex. So precisely, let's index the subproblems in exactly the same way as before. There's going to be one for each budget I and one for each destination j. For a given I and a given j, the value of the subproblem is now defined as the length of a shortest path beginning at 1, ending at j, using exactly I edges with the additional constraint that no repeated vertices are allowed. The one exception being that if j is equal to 1, then of course you're allowed to have 1 at the beginning and 1 at the end. But for the internal vertices in a shortest path, we do not allow repeats. So what do you think? Does this refined collection of subproblems allow us to get a polynomial time algorithm for the traveling salesman problem? So the answer to this quiz is more subtle than the past couple, and the correct answer has switched from C to B. It's still the case that there's a quadratic number of subproblems. It's still the case that we don't expect a polynomial time algorithm. But now that with this different definition of subproblems, they do capture the TSP. Specifically, look at the biggest subproblem. Take I equal to n, take j equal to 1. The responsibility of that subproblem is to compute the shortest path from 1 to 1 that has exactly n edges and no vertices repeated internally. That is exactly the original problem that we started with. That is exactly TSP. The issue is that you cannot efficiently solve larger subproblems, problems with a larger edge budget, given the solutions to the smaller subproblems. The smaller subproblems are just not very useful for solving the bigger subproblems. And the reason is a little bit subtle. Now the hope would be that, like in all our previous dynamic programming algorithms, you can just formulate a recurrence which tells you how to fill in, how to solve bigger subproblems given solutions to smaller ones. And there's even a natural guess for these subproblems what you hope the recurrence might be. Recurrences generally follow from a thought experiment about what optimal solutions have to look like. So you'd want to focus on a particular subproblem, a given destination j, and a given budget I on the number of edges. You'd say, well, let's think about an optimal solution. So what is that? That's a path. It starts at 1. It ends at j. It has exactly I edges. It has no repeated vertices. And amongst all such paths, it has the minimum length. And it's natural to proceed by analogy with Bellman-Ford and say, well, wouldn't it be cool if a little birdie told me what the penultimate vertex k was on this shortest path from 1 to j? So if I knew that the second to last vertex on a shortest path was k, well then surely the length of this path would be the length of an optimal path from 1 to k using exactly I minus 1 edges and no repeated vertices with this final hop kj concatenated at the end. Now, of course, you don't know what the second to last vertex k is, but no big deal. As usual in dynamic programming, we're just going to try all of the possibilities. So we can encode this brute force search as a minimum over the sensible choices for k. Clearly, k should not be equal to j. It should be some other vertex that precedes j. And ignoring some base cases, let's also preclude k from being 1. That's the starting vertex. And of course, pictorially, what we have in mind is we have in mind taking some shortest path from 1 to k. So we'd look that up. That would be previously computed in some smaller subproblem, and then concatenating to it a final hop that goes from k to j. Well, hey, that sounds pretty good, right? Doesn't that kind of sound like maybe this is the key ingredient to a polynomial time algorithm for TSP? So what's the problem? Well, the problem is that we've defined our subproblems to disallow repeated visits to a vertex. So when we compute a subproblem, we better make sure we're respecting that constraint, that no repeated visits are allowed. And if we have in our mind concatenating a shortest path from 1 to k with no repeats with this final hop k to j, well, this might result in a repeated visit to j. In particular, for all we know, the shortest path from 1 to k that uses exactly I minus 1 edges and has no repeated vertices, that path might well go through j, in which case concatenating this final hop kj results in a cycle, a second visit to j. So this bug means that the proposed recurrence is not correct. The recurrence is computing something which in general is less than the actual shortest path length from 1 to j with exactly I edges with the no repeat visits constraint respected. That could be a bigger number than what's computed by this recurrence. And I encourage you to think about, is there any way to fix this bug? Could you propose a different, more complicated recurrence, which was still easy to evaluate, but was actually getting the subproblem value correct? I don't think you're going to find one. So the moral of the story is that this constraint in the traveling salesman problem that each vertex gets visited exactly once, that's a quite tricky constraint, and we're going to have to work quite hard to make sure it's satisfied. The solution we're going to use is in some sense a logical next step from this recurrence here. We need to be able to know more information about subproblems than just where they end. We actually need to know the identities of the vertices on the path used to travel from 1 to k. We need to know whether or not v is on that path. So we're going to look at a much bigger set of subproblems where we remember not just destinations, but also all of the intermediate stops. That idea will translate to a dynamic programming algorithm, not a polynomial time one, needless to say. The details are coming right up.